is simplifying. We can multiply this out. Now, this is much easier to integrate. Using the power rule for integration on each term, this integrates to 1/4 x to the 4th plus x cubed minus x squared minus 6x plus c. Notice that our arbitrary constant c is back because we're taking the indefinite integral here. So, the first method is to simplify the function by multiplying it out and then integrating it with the power rule for integration.
Now let's look at another, more complex problem.
Let's say we've got x cubed times the square root of 2x to the 4th minus 7. Again, there is no product rule for integrals, but this time we can't simplify the function by multiplying it out either. So here's the second method, substitution or change of variables.
This substitution rule is kind of similar to the chain rule from our first video.
To use this rule, we need to take this hunk of a function and rewrite it in a more manageable form. Remember how we can rewrite our square roots? Well, let's do it. Let's rewrite this as x cubed times the quantity 2x to the 4th minus 7 quantity to the 1/2 power. That's better. Now, what we have here is our composite function because it's composed of a lot of pieces that we can break down. Out of this composite function, we need to identify a term that is inside of a power. In this case, that term is 2x to the 4th minus 7. You see where we got that? It's the expression in parentheses raised to the 1/2 power. So we let u equal 2x to the 4th minus 7. So the first step is to pick your u. Then your next step is to take the derivative of u. I know it seems weird to take the derivative here even though this is an integration problem, but do it anyway. You'll see why in a second. So by the power rule for derivatives, du dx equals the derivative of 2x to the 4th minus 7, which is 8x cubed.
So du over dx equals 8x cubed. Remember, du over dx is just another way of writing the derivative u prime. Now here's where things get a little tricky. Let's simply treat dx as if it were a number and solve for it in this equation. So we're basically just trying to get dx by itself on one side of the equation. Now just do as you're told. First, multiply both sides by dx to get the dx out of the denominator. Then divide both sides by 8x cubed, and we end up with dx equals 1 over 8x cubed du. So you've got your dx, it's 1 over 8x cubed times du.
Now let's substitute this value into our original function. So we plug in 1 over 8x cubed times du for dx. We also plug in u for the 2x to the 4th minus 7, because that was the u we picked earlier. Subbing in, our equation becomes the integral of x cubed times u to the 1/2 power times 1 over 8x cubed du. Now, look what happens. The x cubed in the numerator and denominator cancel each other out, and we're left with the integral of 1/8 u to the 1/2 du.
Notice that everything is now in reference to u.
Me?
No, u. Because this is the case, we can apply the power rule for integrals using a u instead of an x. It is important to point out that basic substitution or change of variables only works if, after substituting in for dx and simplifying, as we have here, there are no x's left in the equation. If you've got x's left, you need to use a more advanced method. But we've got no x's, so we can use it. The whole idea is to convert a bulky function raised to a power into a nice basic variable raised to that same power.
This integral becomes 1/8 u to the 3/2 power divided by 3/2 plus c. Now use some algebra again and invert the denominator and multiply it by the numerator. This equals 1/12 u to the 3/2 plus c. Wait a sec, we've still got a u in our answer. Teacher may not like that. No sweat. We'll just substitute 2x to the 4th minus 7 back in. This will give us our final answer. Since we let u equal 2x to the 4th minus 7 earlier, our final answer becomes 1/12 times 2x to the 4th minus 7, quantity to the 3/2 power plus c.
Just so you know, we could check our answer here if we wanted to by taking derivatives using the chain rule. We won't take the time to do it now, but it might be a good rainy day activity for you and your friends. And hey, sometimes it's a good idea to check your answers on hard problems, especially during a test.
Let's try one more example using substitution or change of variables. Let's integrate 2x over the quantity x squared plus 3. Since there's no quotient rule for antiderivatives, we know right away that we might like to rewrite this as 2x times the quantity x squared plus 3 quantity to the negative 1 power.
So, our composite function is 2x times the quantity x squared plus 3 to the negative 1 power. Our first step here is decide what u will be. Again, we look for a term that is inside of a power. In this case, we'll let u equal x squared plus 3. The derivative of u, or du, over dx equals 2x. Now solve for dx, just as we did in the last example. This is like a side problem which you do by multiplying each side by dx and then dividing each side by 2x. We get dx equals 1 over 2x times du.
Now substitute what we have back into the original function, 2x times the quantity x squared plus 3 raised to the negative 1 power. And what do we have, you ask? Well, we just found dx, and we know what u is, so we can just plug in those values. First, we sub in the u for x squared plus 3, and then 1 over 2x du for dx. Now simplify. The 2x in the numerator and denominator cancel each other out. This leaves us with the integral of u to the negative 1 times du, or 1 over u times du. So, u is now the only variable.
Next, we'll integrate our rewritten composite function of 1 over u times du. What to do here? Well, we'll just pull a little trick right out of thin air. Integrating this, we get the natural log of the absolute value of u. Remember that old rule? The integral of 1 over x equals the natural log of the absolute value of x plus c.
Finally, we just need to rewrite our answer in terms of our original variable x. So our final answer becomes the natural log of the absolute value of x squared plus 3. Since x squared plus 3 is always positive, we can drop the absolute value here. And that's your answer. That's it for substitution and change of variables.
Well, now we're finished with the candy-coated world of calculus, part 2. We've come quite a long way from where we began. Remember when we talked about critical points and all that came from them, increasing and decreasing functions, local extrema, concavity, and the like? We even touched on derivatives and distance, motion, velocity, and acceleration. And then there was the antiderivative. First, the indefinite integral. They were so cute. Not to mention the definite integral. So strong and decisive. We could use them to find area. Who else could do that? Well, those messy Riemann sums could, but not as easily. And then there was the fundamental theorem of calculus.
You'll have to excuse him. He was really close to a lot of those concepts. Well, anyway, that's it for the candy-coated world of calculus part 2. We've been a lot of places, we've seen a lot of things, but most of all, we've had fun. And we did calculus. And that doesn't happen but once in a blue moon. So if you have any questions about what we've covered, feel free to call us at 1-800-238-9669. We'd like to know how your class went.
Well, we have come to the end of the videotape. I hope you've learned something about calculus and relativity. Well, this is a place where we must say goodbye. And so, goodbye.
I live in a hypothetical world, and I'm not going to take it anymore!
Makes no sense to me. If the derivative of the antiderivative equals the original expression, then you were right!
If the derivative of the antiderivative gives you abdominal pain, then you need to see a doctor.
But you are a doctor.
Well, I guess there's no hope for you.
I can't divide by 0! What kind of a world is this?
Once again, there's no need for an arbitrary constant c. It would just get subtracted out anyway, you know, by the man.
Yeah, dude, we get the point.